Good morning, class. Today is the 21st of January. Already the month is almost over, so it's kind of crazy how fast time goes by, isn't it? We're looking at lesson 1-6 today. And you should be able to have completed quiz 2 by now. All right, so you definitely wanted to get on top of that and get that started if you haven't already. But the objective that you need to have completed is 1-6 after today if you haven't already done that. So let's go ahead and get quickly started. All right, so 9530. All right. All right, I have a quick question for you. Just something that, just gives me assessment about the direction so I can tell my colleagues about the delivery method. I mean, do you like this, like where we're meeting together? I mean, it forces you, of course, to have a set time to come to class, but it does allow you to have the instructor working with you. And I just wanted to know your opinion, because obviously it's important that you share your thoughts. I mean, anonymously, obviously. But I think it's really good that we have a structure. Now, I know some instructors make the students show their video. Perhaps maybe that's not an extremely bad idea, because the fact is some of you don't stay. Once you log in, once you sign in, once you see that 9530, you just leave. Yeah, you could do that. Look at 4 responses. I haven't even gotten anybody to respond. I mean, there's 2 people responding, not 3. But I have this poll, and I'm just trying to get an idea about some of the thoughts you have in delivery for instruction. Because would you have wanted to do this all by yourself? I mean, that's a big task to undertake. When you're talking about having the need to teach yourself, that's demanding. And I think that this is the alternative. This is kind of the future, if you per se. I mean, I would think this is the way I would like to instruct. I mean, we don't have to be in a brick and mortar class. And I don't know. I mean, by the anonymous poll there, I mean, there's one person who hasn't responded yet, but I'm going to go ahead and show the responses to everybody. So it's pretty evident that this is a delivery structure that's working for you. And I will report that back to, of course, my superiors. Tell them, some of your perspective, like this is what you are looking for in a class. So I'll just close that out. But anyway, I think it's good that we're meeting together, and I appreciate your feedback on that. So today we're going to do 1-6. It's probability. All right, probability. What's amazing about this course is that we go from talking about, the coordinate plane system. That's what we did the other day, right? The coordinate plane system on lesson 1-5, and then we talk about probability. Basic probability, that is. Because what are the chances? Now, that's how 21-6 is designed as well, by the way. 21-6, it shifts gears a lot. And I would encourage you to absolutely take me for 21-6. I'm pretty solid with that class. I mean, yes, it's harder. It's way harder than this class. I have many students who have done well in this course and then take me for 21-6 and do poorly because they just totally don't respect the class. The class is demanding, but if you dedicate yourself and utilize the resources that I'm providing, there's no reason for you to have anything but an A. in my course. But anyway, I just wanted to reinforce that this is how 2106 is. We're going to talk about probability towards the end of the course in 2106, and it gets interesting. But you probably dealt with probability a lot. Matter of fact, even when you watch football or watch any sporting event that involves flipping of a coin, that is probability. Now, the reason why is because a coin is used because it has a 50-50 chance of leading to any one result, and that is either a heads or a tails. Now, that's an even chance. But imagine you had a coin that had two sides that were both heads. Then there's an unlikely chance that a very strong unlikely chance that you're going to get a tails if both of them are heads. It's impossible, matter of fact. And then, of course, it's with certainty that you're going to get a heads if you're flipping a two-sided coin with both heads. So that's how probability works in a sense. We use a die a lot of times playing different games. Matter of fact, you play like something like craps on, craps is the one that you roll into dice. There's two dice, and you're trying to get, lucky seven. Seven is the most probable number you can roll. And you see it in a lot of movies. You see it in the casinos, obviously. So probability, landing on something, each side of a die is one side of six sides. So we have a 1/6 of a chance of landing on any one side. And landing on something means it's faced up, right? So where you can see the face of it on the top. So that face is then considered a side, and that side is then 1/6 of a chance of being shown. So now that's why it says that it's hard to read, but that says 1 in 6 chance of landing on any one number. Now, cards are another very high level probability type game, like when you play blackjack and just raising your hands. I mean, how many of you ever gone to the casinos? I'm just curious about. I'm going to look at the class. See how many of you went to the casinos. Oh wow, nobody. None of you are old enough to go to casinos. Okay, I mean, or maybe you never just did it. I went to Atlantic City. I've been to Atlantic City. I've been to a few places. I haven't gone to Vegas. That's one of my things I'd like to try to do is go to Vegas. One of the bucket list items. Because I just want to feel that energy. It's the city that never sleeps. I mean, so just feeling that energy is probably pretty powerful. But I'm not that I would ever go ahead and gamble. I'm not a big gambler. I mean, I'll go into a casino and I'll bring 20 bucks. Sometimes I can get that up to about 500. Sometimes I get lucky. But then other times I'll walk away with nothing. And most of the time it's walking away with nothing. And like it's just crazy how you can change money real quick into high, but you can also lose it really super fast. And the house always seems to win, and because the odds are stacked against you, by the way, in winning. So your probability is very low to win. Anyway, so when we're looking at these different things, there's a formula that you have. It's like the number of outcomes that can occur with the total number of outcomes, and that's like that rolling a die, probability of rolling a 4 with one die, and that is 1 out of 6 chance of rolling a 4. So we say that it's 1/6, right? P of 4 is 1/6, or is 1/6. So that's how they're wording it. But I mean, but that's how it is with probability. This is computing probability. Now, this doesn't really get into too much more other than we get into what's called empirical and theoretical probability. Theoretical probability is, in fact, that which we've been talking about, like 1/6 of a chance. That's theory. All right? It's theoretical because it's what you expect to be an outcome. But empirical probability is rolling the die a bunch of times and let's say 100 times and recording how many times that 4 comes out, like rolling that 4, right? Because we say that rolling a 4 is 1/6 of a chance, but what about if we rolled it, 100 times and never did we get, um, a 4? That means that that die is most likely either tainted, its balance is off. In other words, it's not constructed properly. So that's the empirical, is the testing of the die. We go through a lot of testing in society. You have to test cars, for example, to make sure that their safety is there and things like that. If you were together in a class, we would do an experiment with, it says a standard playing card, a dime, and a scotch tape. You would flip the card, all right, with a die or with some dime taped to the floor, or not taped to the floor, but taped to the card with a dime on it. So you go ahead and throw the card and see how many times it lands faced up. All right, because the point is, if you flip the standard card and let it fall on the floor, the theoretical probability of landing face up is 1/2. We can change the probability by making one side heavier, and that's what we would most certainly be doing. Then it would make sense to compute the empirical probability to see what outcome occurs. So interestingly, you can actually run this for yourself if you were to run a standard test, and that is empirical probability. Now, I went over that with you several times to go ahead and make sure that you understand the difference between theoretical and empirical. Are there any questions on the difference between theoretical and empirical probability? All right, we have a quiet class. That's okay. I mean, if you don't have any questions, then I don't want you to force it. But all right, so you know that theory or theoretical probability is the obvious standard, what you think of when you think of computing outcomes for a certain event, and then empirical is testing that which you think might be the outcomes. And give yourself an example. Theoretical probability of rolling a 4 on a standard number die would be 1/6 chance of occurring. That would be theoretical. And then empirical is then saying in your description, empirical is like rolling it 100 times and seeing if 4 is 1/6 of a chance. Now, what is 1/6? 1/6 is 0.16 continuous. So if you were to take a calculator, right, and do 1 divided by 6, because that's what it is, then it's 1 or 0.16 continuous, and this repeats. All right, repeated decimal. And then, of course, you can turn that into a fraction as well. Look at that. See, boom. And it even writes it that way. So interestingly, it has different ways of being displayed. And then, of course, you can say it's approximately 17%. All right. So anyway, we continue to look at this. You can do the book, right? I mean, you notice how I'm using the book in a chance of showing you vocabulary, giving you examples, showing you different things. Of course, I'm not working out the problems. If you want to look at the problems and you want to complete them, then by all means, you're more than welcome to. However, we need to look at Alex, because Alex is where you're being assessed. So I'll take a look at a couple problems from Alex now. All right, now what is this question asking? It says a bag of 6 balls labeled A, B, C, D, E, and F. One ball will be randomly picked, and letters will be recorded as outcomes. All right, or as the outcome. So give this sample space description by, describing all possible outcomes. Then give all of the outcomes for the event of choosing a letter A or Z or C, excuse me. If there is more than one element in the set, separate them with commas. So now sample space. Now, when we're talking about the sample space is all the letters. That's the sample space. So we just have to just type in what we have. So A, B, C, D, E, F. And the event of choosing a letter A or C is A or C. All right, see how easy that is? All right, that's pretty straightforward. So in this case, a number cube face is labeled 1 through 6. So then that would be 1, comma 2, comma 3, comma 4, comma 5, comma 6. And then it says then give the outcomes for events of rolling a number less than 5. So that's going to be less than 5 is 1, 2, 3, and 4. This one, same idea. So it's 1 through 6, and then the outcomes are event of rolling 1, 3, or 4. Then you would have 1, 3, 4 here. So I'm not going to do that one. Now it says a spinner with 6 equal side slices, right? 3 red, 1 yellow, and 2 blue. So that's what you're seeing right here. The dial spun and stops on a slice at random. What is the probability that the dial stops on a red slice? Well, unfortunately, this doesn't ask us to make sure to reduce, unfortunately. So you could put actually 3 out of 6 sides or slices and you get it right. I would encourage you to reduce your fraction to 1/2. So you have marbles. They're all right here. What is the probability of getting a yellow? So that's 2 out of the 6 marbles. Now I'm going to put 1/3 because that's the reduced value of 2/3 or 2/6 is 1/3. And so I'm going to write down 1/3 and you're going to get a right answer of that as well. So you can write down 2 out of 6 or 1/3. I'm preferring that you write down 1/3 because good practice of math is always to reduce fractions, right? So this one says, what is the probability that the dial stops on a blue slice? And that is 2 out of 10. All right, I'm going to write that down as 2 out of 10, and I'll show you, because some of you can't visualize what I'm doing. If I see 2 out of 10, can't 2 go into both of these? So then that really would mean then 1/5. So I'm going to take that and do 1, and I'm going to take this and make it 5, because 2 goes into 2 one time, 2 goes into 10 5 times. Although 2/10 would be accepted, which I get annoyed by. All right, so now what is the probability that the dial stops on a yellow slice? So this is the same idea, right? And this time I'm not going to reduce it only because, yes, it will accept it, unfortunately. All right, we got enough of that. We've done that several times now. What is the probability that it's a red? It's going to be 2 out of 6. It's the same as the other one. All right, now the drawer is filled with 2 black shirts, 7 white shirts, and 11 gray shirts. One shirt is chosen at random from the drawer. Find the probability that is not a black shirt. All right, so that means if it's not black shirt, that means you have to, first of all, find the total number of shirts, and that's going to be 9 plus 11 is 20 shirts. So then not a black shirt is going to be 18 out of the 20 because 7 plus 11 is 18. And again, unfortunately, they'll accept an unreduced fraction. See, so this gets into the idea that you got to add them now together. So half the large fish are red, all right? One fish is selected randomly. Find the probability that there is a large red fish. Now, here it is. They said that half of the fish are red. So that means there's 5 red fish that are large. So you'd put a fraction of 5 out of the 15 fish collectively. An organization will give a prize to a local artist. The artist will be randomly chosen from 10 painters, 3 sculptors, and 5 photographers. What is the probability that the artist chosen will be a sculptor or a photographer? So sculptor or photographer means 8 out of the total of 18. All right, and this time I'm going to reduce it. All right, I'm going to go ahead and reduce that down because let's see, can't 2 go into both of those, right? So I'm going to reduce this time. I haven't been reducing the last couple, but I am reducing this one. If I'm going too fast, let me know. I mean, some of you are not good with fractions, so if you don't say anything, it means that you understand what I'm doing. All right, now this one's like same thing with the drawer. They have 7 black shirts. I mean, this time you have what, 22 shirts all together, not gray. Means then it's 12 out of the 22, and then reduce your fraction. All right. Now here's something I wanted to get to. Okay, now a spinner below shows 5 equal slices, sided slices, whatever. Tammy spun the dial 1,000 times and got the following results. That means she was doing an experiment or empirical probability when she has this. So fill in the table below. Round the answers to the nearest 10. From Tammy's results, compute the experimental probability or empirical probability of landing on white. So it's 582 out of 1,000. So we would go ahead and put, and it wants it in, it wants to round your answers to the nearest thousands. So you obviously going to have to put in the values into a calculator. So we're going to go ahead and put down fraction of 582 divided by 1,000. Now that's very small for you, so I'll go ahead and blow it up real quick. All right, and here it is. All right, and then we're going to hit enter. Now that's reduced to fraction, but we want it as a decimal, so we're going to hit the S to D button. So that's 582, 0.582, right? So let's go ahead and put that. And it says nearest thousands. So this is tens, tenths, hundreds, and thousands. So now, assume the spinner is fair. Compute the theoretical probability of landing on white. The landing on white is 3 out of 5 slots. So we would go ahead and do 3 divided by 6. Excuse me, 3 divided by 5, excuse me. All right, so it's 60 or 0.6. 60% is what I meant by that. You know what? I'm just going to put 2 zeros just to show you that I could. Assuming the spinner is fair, choose a statement that, below that is true. Now, here's the golden ticket with this. The more times you run the experiment, like 1,000 times is pretty darn high, by the way. That's a lot of times you've thrown this spinner around. Imagine you sitting there and flicking this arrow so it can spin, because that's how you do it, and then having it spin and then landing on something, would you want to do that 1,000 times? I don't think so. But Tammy did, and of course, I mean, this is, I mean, my opinion, that they didn't really do that. They just had a computer do it, but because computer can randomize that event happening. So anyway, the larger number of times you do it, the closer and closer these two numbers get together. Like, look how close that is. I mean, that's only off by 2/100ths of a, not even 2/100ths of a value off from each other. 2/100ths of a, you know, so that's not even that bad. And if we turn it into percentages, it's only off by 2%. That's not even, that's not a lot at all. Okay. So it says the smaller number of spins, that's not right. The larger number of spins, the greater the likelihood that the experimental probability would be close to the theoretical probability. That's what you kind of always after. You're after that kind of an output. Now, the experimental probability will never be close. That's not true. Now, the smaller number of spins you do, the greater likelihood that they're going to be farther apart, not closer together. So if I spun this one time, here's an example of a very narrow margin. I'm saying, if I spun this one time, I land on a black. That means from my experiment that there's a 0 chance of landing on white if I only spun it one time. I go from 60% chance of getting a white to 0% chance of getting a white. What about if I spun this 10 times and, wow, miraculously, I landed on only gray and I only landed on black? Only by mere chance that would happen, but it does happen. That means after only 10 experiments, then I go ahead and land on, there's no chance of landing on white. Now, but then I start spinning this more often, like say 100 times. I am most certainly going to land on white many times because there's a lot larger chance, all right, of landing on a white than there is a black and a gray, all right? So that's what we're looking for. And that explanation and that discussion really deepens your thoughts about what an experimental or empirical, I'm putting that together because obviously that is the word that I really wish they would say empirical rather than experiment, you know, because that's experimental, right? And in here it's is empirical, and that's empiricals right there. And I'm like, experimental and empirical are applied to the same exact concept. So understand that empirical probability is running an experiment, and that's why the Alex uses that word to go ahead and dictate empirical. All right, so I'm just letting you know. So I had a great discussion about that, and I think that really should hit it home and resonate a lot. Now I'm not going to have as big of a conversation about it, but here we have 25 times. That's not a lot of times. All right. Now we're looking at the experimental probability of landing on white, and it's 25 times, so it's 11 out of 25. So again, I grab my calculator and I just simply do. I do my 20. What is it? 11 divided by 25, and I get 0.44. All right, now assuming that the spinner is fair, compute the theoretical probability of landing on white. It's 4 out of the 10 times. So we're going to look at 4 out of 10. So 4 divided by 10, that's 0.4. Now, again, the language for this selection is going to be the same as it always is. It says the number of spins increases. We expect that the experimental and theoretical probability to be further apart. That is not true. It is going to be closer together. May not be equal. Of course, they might not be equal. All right. And of course, then we continue that idea. All right. Now, do you need me to go over that again? I've gone over two of them right now. All right. I'm always speaking up, so I'm going to assume that you guys understand. That's a bad thing to do for me, is assume, but I'm not going to take and absorb so much of your time. This is a quick class. I mean, always seems to be that way. All right, the spinner has with 10 equal sides. What is the probability of dial stops on a yellow slice? Is 2 out of the 10, and that's we've already done before. So 2 out of 10, and of course that's not reduced. I could answer these very quickly, but there's no sense in me going real fast and just answering it for my sake. Now this one right here, this one's a little different, okay? Now it says the marble is randomly chosen from each bag. List these events as least likely to most likely. Choosing a blue marble from a bag A. Now we got to actually run this, run the probability for each event they call out. So it's a little tedious. So we have 4 out of the 16. So we have 4 divided by 16. It's going to give us 25%. So it's going to be 0.25 for event 1. So we can say E1. Now E2, let's look at E2. It says choosing a green marble from bag B. Now bag B has no green marbles, so there's a 0 chance of that happening. Event 3, choose the orange marble from bag B. Then orange is 3 out of 10, and that's 30%, or 0.3. Event 4 is choosing a blue marble or orange marble from bag A. Now bag A has blue and it has orange, so choosing that means you're going to choose 16 out of 16 or 1, which is 100% of a chance of happening. So therefore, putting these in least likely would be event. Event 2 is least likely to occur. Now the next would be event 1, because we have event 1 at 0.25. So we're going to put 1 here. And then we look at it, and event 3 is then the next most likely because it's 30%. So that's event 3. And then we have most likely to occur is event 4. So then we check it, and we get it right. Okay, so it's a matter of computing the probability for each event, and then comparing the event's values or the percentages. And that's how you do that one. And they give you another one like that one. All right, very similar. You would run the same exact concept. All right, and again, if this is needed, you can go ahead and review this. All right, but I'm not going to go ahead and do it exactly. It's exactly the same question except for different numbers and different things. Rather than marbles, it's pens. All right, so that concludes then the lesson for 1-6. Now I'm going to double check. Did everybody sign in? All right, Cody, you're not here, are you? All right, Cody's not here. All right, and everybody else signed in. All right, sounds good. All right, are there any questions? Because now we've completed 1-6. You guys are free to now complete 1-6. You guys could have done 1-6 probably before this, but probability is kind of fun. I mean, I hope that you enjoy probability. If we were together as a group, we would have done the experiment, perhaps maybe, or we'd have worked on our work. So if you have any questions, you can stay behind, or otherwise, you guys have a great weekend and be safe.